first of all, thanks for coming. Darren invited us and then he tells me he wasn't expecting anybody to turn out. So I don't know if I take that as a compliment or not. So as a quick show of hands, how many of you call yourselves engineers, just out of interest? Geologists? Yeah. Geophysicists? Other? Yeah, very good. Okay, so that's useful. So I'm going to give a presentation which is kind of more of a philosophical presentation rather than nuts and bolts of how to do. And I guess the points I want to leave you with are, well, one, probably to tell you something that you already know. Two, to encourage you to talk to each other, and particularly talk to people in disciplines other than your own. Three, to make use of all of that expensive and valuable data that you gather. And to respect the geology. I think that's probably the most important thing. So when we talk about a ground model, I think lots of people have in mind a completely different thing, and that's absolutely okay. For me, a ground model could be anything from a fully quantitative GIS-based 3D or 4D type model you can interrogate, all the way back to some of the classic models that Peter Fuchs was putting forward, which are kind of hand drawings. In essence, this is a synthesis and a representation of our state of knowledge of the ground conditions. And so for me, that's what the ground model is, and how you package it up is absolutely up to you. But the main thing is that you're making use of the data that you have, and you're using this to develop the project in the most efficient manner possible. So according to the SUT guidance notes for offshore wind, the ground model is a series of written reports, it's a database, and it's a geotechnical risk register, or an identification of the potential constraints for foundations. But in essence, it's not just a static thing, it's the update of your state of knowledge and the synthesis of the ground conditions, and information that's going to be relevant to the proposed development that you're installing. Trevor Evans had a really nice 2010 ISFOG paper, I encourage you all to read it. In this, he lays out the purpose of a ground model and says, really, this is going to be a predictive and flexible model of ground conditions and hazards and constraints. This was developed for offshore oil and gas developments, but it equally works for large renewable developments as well. And its purpose is really to inform effective wind farm layout planning and foundation design at all stages through the process, and to make the most of those expensive surveys and site investigations you're performing. So one, you identify potential constraints and engineering challenges, and two, also to make the most opportunities that you can with the data that you have. So offshore wind, particularly looking at round 3, there's a number of reasons why a ground model approach is warranted and useful. And partly it's because we're looking at kind of unprecedented large spatial areas with lots of foundations, challenging infrastructure, interconnector arrays, a whole range of water depths. Maybe you need to consider multiple different foundation concepts. And very complex geology, particularly in the North Sea, in an area that has experienced previous phases of glaciation, deglaciation. Some areas which are now submarine were formerly, during previous sea level stands, actually exposed, may have been loaded by significant amounts of ice. So laterally and vertically, soil conditions can be very variable. And in many cases, much more variable than the deep water developments that Trevor Evans talked about in his 2010 ISFOG paper. There's a number of other considerations that we need to bear in mind as well: environmental, metocean, a range of other things. I won't dwell on them too much. But the key thing is, and you'll all be aware of this, the vast amount of data that you have to deal with. So one of the risks, it's not just a risk to the development from the ground conditions, but there's a risk of wasting and not using those data. So we need to think about clever ways of using those data. In some idea, here's a very simplified view of the seabed geology of the North Sea. This is very, very much simplified. And some idea of the range of, say, number of laboratory tests or samples in the far right column that you might be anticipating for a round 3 wind farm. So a lot of data to be dealt with. So some overviews of some of the geophysical and geotechnical data sets that you might deal with. So the desk study stage early on, maybe you're working with public domain data, maybe legacy surveys that have been performed in the area, putting together existing public domain sampling, and then looking at site-specific surveys for foundations, for reconnaissance, for inter-array cables, for unexploded ordnance, and then looking at surveys after installation to look at the effects of things like scout. So a lot of different disparate data sets that need to be integrated and interpreted usefully. And so here's just one example of an offshore wind farm, the Dogger Bank wind farm, a 2D seismic profile here from Carol Cottrell's paper from a couple of years ago. And here you can really see the depth in meters is on the top right there, going down to about 60 meters. Quite how variably, laterally and vertically the soil conditions can be. So if we're performing CPTs, you could build a ground model purely on a statistical basis and have a regular grid of CPTs, but maybe that regular grid isn't going to be the most useful thing to characterize the ground conditions we have here. So how variable would the CPTs, for example, be between these three different locations? Well, probably quite different. And so I guess one thing I want to encourage people to do, and I'm sure you're doing this already, but is if you're an engineer, to make use of geophysical, geological data and use this to inform the planning of where you're putting CPTs and boreholes. Use this to inform your strategy for have you sampled all of the units in the site? Are there areas perhaps where deeper stratigraphy is coming shallower in some parts of the site that you could take samples in shorter boreholes? Here's some slides from Dave White at the University of Southampton showing 3 cone penetration tests that are just separated 2.5 kilometres apart, but showing some significant variability. He also makes the point in a separate OSCE presentation he's given that the CPT is also only characterising a very small amount of the soil, whereas your piles may be much, much bigger, so 5-metre diameter. So maybe twin CPTs that are fairly close together allow you to get some idea of bounding the range of very local variability as well as the site-wide variability. Okay, so what I mean by a ground model here, again, just to reiterate that, is this is the model that's helping us understand how the site came to be, what geological evolution it's gone through, and using all the data that we can. And I think ultimately, I mean, there's a fairly simplistic block model that I'll use here, but how you portray that, whether it's done in crayon or pencil or in GIS, if it's done in a mechanism or a way that can communicate the constraints and also the range of soil conditions, then there's something really useful there. So you'll be bringing in public domain information, so this will be information that surrounds the site, and also building on analogous sites. So you might think about sites that are not geographically close, but have undergone a very similar geologic history, can help you interpret and understand the data that you have at your site. Geophysical data, which give us some idea of the lateral variability and vertical variability in geology. One of the important points to note here, though, is it's worth having that communication early on in the project between geophysicists, geologists, and engineers, such that when horizons are being picked, they're not just picked because they're an easy, high impedance reflector to pick, that they've actually been thought about. Might they actually represent an interface between geotechnically, might they represent an interface that could be geotechnically variable, so maybe a clay to sand interface, normally consolidated to an over-consolidated clay interface. Bringing in a whole range of different geotechnical data, bringing in metocean data as well, and this becomes particularly important if, for example, the wind yield assessments change for your development, so you maybe need to think about a different arrangement for the turbines on your site. This is where the ground model is useful, and you can revert to that and think about updating your conditions. Bring in the results of engineering analysis, and typically this will all be hosted within some sort of geospatial database, usually GIS, but other packages are available. So for my mind, the ground model, first of all, is kind of a documentation of how the site came to be. So we might take a site and look at the variability of bedrock. So what's the extent of weathering? How does the depth of bedrock vary across a site? This erosional surface in the North Sea might have been caused by one of the early phases of glaciation. Subsequent to that, well, let's say we've got some glaciogenic till deposits here, which may be littered with boulders, but might be concentrated in some parts of a site and not in another. So these could preclude the driving of monopiles. You could get very variable soil conditions, so this might be a time when our site was under subaerial conditions. So we could have river channel infill deposits, sand in the axis of the channel, maybe clay on the overbanks. And then at the present day, maybe we've got gravelly and sandy seafloor, which is prone to sediment mobility and sand. So it's kind of a typical sort of North Sea site, just shown in a cartoon. But that ground model then can be used as a communicative tool to start to explain some of the potential foundation constraints. So we start to translate that geology into engineering considerations. So in terms of building that, typically you'll perform a desk study at the beginning that will give an overview of the previous experience you have in the area, bringing together all the available data that might exist, and create a kind of an initial, maybe conceptual ground model. And that could be used initially for screening foundation types, and then used to design and optimize geophysical surveys. And this is very much a kind of a simplified approach: geophysics, geotechnics, engineering. Often there will be multiple phases of reconnaissance geophysical survey, and it's really important to take advantage of opportunities as you go through. If you are taking samples, for example, for environmental purposes, there's an opportunity also to perform geotechnical analysis on those. So this is where it's important for disciplines to talk to each other and take advantage of opportunities as you go. So it's not just a stepped process, and the ECOSIGG guidance notes make that quite clear. And the ground model can be presented in all sorts of ways. This is just away from Reynolds et al. In 2017, whereby you can see the top panel here. Here's a geophysical profile which is annotated with coloured horizons. So these demarcate the tops and bottoms of units which are determined based on their acoustic character and based on spot geotechnical tests and measurements to have distinctly different soil conditions. So you can use your ground model to perhaps put in your boreholes like this and look at where you have sampled to make sure that you have actually appropriately characterised all the different units in your site, work out perhaps what you're missing. The geophysical data can be used to inform your site investigation strategy, and often maybe you want to acquire more geophysical data than you initially think, because you maybe have to update foundation layouts at a later stage, and having more geophysical data might be relatively inexpensive in the overall costs instead of having to mobilise another vessel for another survey later on. It's particularly important quite often, layouts will change as something is found during a survey or site investigation. Often CPTs and boreholes are going to be performed at turbine tower locations for wind farm developments. But what about the jack-up barge that's going to be installed in those monopiles? Where do you get that information from? Do you need to perform extra CPTs? Or have you got sufficient geotechnical data you can integrate with your geophysical data to confidently extrapolate away from those locations where you do have geotechnical measurements? This is where the ground model has a key part to play. And so I guess kind of a traditional approach to this is integrating your geophysical, your geological, your geotechnical data, and to create soil province maps that laterally demarcate areas of similar vertical, different soil conditions. So for example, here you might have a soil province which is mostly representing the infill within a channel, which would be quite distinct from somewhere outside of that. So these sorts of approaches are used, and can be used early on for screening different foundation types, could be used for cost comparisons. This should be accompanied with something like a geotechnical risk register or a foundation constraints register, which lays out a list of the different types of features, the constraints they might pose, and an identification of where they occur within the site. And a recognition that different features may affect different foundations or different structures in different ways. So, an inter-array cable will have many different constraints than say, a driven monopile. I guess some of the issues with this type of approach are, though, the soil province model doesn't necessarily explain the geology very well. It's very rare that geology has these kind of physical boundaries that stop. Usually there are gradational changes, let's say in the nature of the fill, which may be more sandy and progressively more muddy as we go laterally. And so it's important to be aware of that, to understand that, and so your soil provinces and your soil profiles that relate to those need to have appropriate bounds on them. And so the geologists need to work with the engineers to identify what are appropriate bounds. You don't want to provide such wide bounds that you have to go for a really conservative design. So that's where different approaches can work, and this is where geostatistical approaches are very helpful, because they're kind of respective of the geology. So there's advances being made in making more of geophysical data If we look at the oil and gas industry, we look at reservoir depth and interval. The quantitative use of geophysics is something that's routinely done. So rather than just mapping horizons that bound different areas of different depths of acoustic character, basically an inverse modelling approach is taken to the seismic data to try and back out physical properties. And this is usually with oil and gas with a view to get things like porosity and permeability. But there's a number of opportunities with high resolution seismic data to try to get to quantitative geotechnical measurements. And so I'll show some slides here developed by Mark Vardy at Sand Geophysics, and we worked on this when he was at NOC, looking at a trial seismic inversion project at the Walney 1 wind farm site, trying to add extra value to the geophysical data. It's typically, we have to pick these horizons, these interfaces, but we ignore all the good stuff in between, all the phase and the frequency content and the impedance. So here's a site where we have some shallow cores, less than 6 meters, some deep CPTs, up to 40 meters below seafloor, and some single and multi-channel seismic reflection data. We're just going to focus on the single channel data here. But it's a site with very complex stratigraphy. Okay, so here we have one of the 2D single channel lines. So you can make out, let's see, maybe if there's a button here. Just up here, so we have the seafloor up here. And then down here we have kind of the weathered top of the Triassic Mercian mudstone. So we can pick out some really irregular eroded surfaces. This is the bottom of a till deposit, which is infilled with over-consolidated Ørsted sediments. You can see all sorts of other features in here. You can see some prograded units in the top one. These are prograded sands. And at the top is a kind of a very muddy seafloor. So it looks like a flat seafloor, but there's a lot going on underneath, a lot of complexity. So the approach that was taken here was basically to say, well, if we have a CPT at this location, can we use machine learning approaches to try and train an inversion algorithm to try and predict what's happening at another location a few kilometers away and get a pretty reliable prediction of what the CPT response should be? So that's kind of the question and the approach that's taken. I won't drill into the details here. I can pass on some papers that dig into this. But in essence, we train the algorithm with the input here of cone resistance, and we use all of the content within that seismic data. We look at the impedance, the amplitude, and the instantaneous frequency that's preserved within the seismic data, and use that combination of things with a genetic algorithm to try and, first of all, train the algorithm. So we start with FO2, and we're going to predict about 1.5 kilometers away what's going on at FO4, another location where we have a CPT. So we can work through the inversion process, and then we can start to make a prediction of what the impedance would be, the density and porosity based on empirical relationships with velocity and impedance. And so these are starting to get to physical properties that oil and gas exploration use, but not necessarily that we would use in geotechnical purposes. And then from that, basically train the model using one CPT that we've put in. So here now we're starting to convert that seismic data into cone resistance and sleeve friction. And shown here in black is the predicted CPT trace. You can make out hopefully a little grey window either side of this. So this is based on 100 runs through the inversion. And then the red squiggly line is the actual CPT at that location. So Mark Vardy's trialled this on a number of different sites. But the key thing here is there's a need to train this on site-specific CPT data. So this isn't just an empirical relationship which can work universally. So you do still need this geotechnical data. But over a few kilometers, we're starting to be able to get a pretty good prediction of what the CPTs are going to be. So here is basically what the model did before training, and this is it afterwards. So measured cone resistance versus the predicted cone resistance. There's still quite a lot of scatter. There's still work to be done to work out, would you ever use this for design? Perhaps not, but if your layout changes, then you have much more confidence. You have much more quantitative information in your geophysical data, than you have from just looking at wiggly lines. So that's just one approach. There's a range of different approaches for building ground models. As I said, it could be done as a cartoon sketch, and if that gets the message across, then that's good enough. You can use all the quantitative information in your geophysical data. It's also worth bearing in mind, though, that sites can be very dynamic. So here's an example from the Robin Rig wind farm, looking at evidence of scour that's occurred following installation of monopiles. And in places like the Irish Sea, very rapidly within one tidal cycle, significant amounts of sediment can be eroded, and that will change the way your foundation will perform. So this ground model needs to be updated. For oil and gas developments, ground models are being updated to include decommissioning stages as well. So it provides you with an opportunity to manage and make sense of large data volumes, just some more evidence of scour and then deposition around the monopile. As I said, it's not really showing too much of the nuts and bolts, but hopefully it's an overview of the philosophy behind the ground model, why it's important to respect the geology, because that sets up the site as it is. But there's a need to communicate that geology to engineers, and for engineers to also communicate what's important, what represents a constraint, what horizons might actually be appropriate to pick, rather than just the easiest ones. So ground models take many forms. There's a compelling need to integrate effectively all of the expensive data that you're gathering. And for me, the ground model should allow you to screen solutions, identify hazards early, provide a good communication tool to explain the variability across a site, use the geology to explain potentially anomalous geotechnical test results, to rapidly update layouts if necessary, and improve confidence in design, particularly if you need to provide information for, say, jackups away from where you have performed a CPT or a borehole. So that's it in a nutshell, and I think Mike will pick up and drill into some proper nuts and bolts of geotechnics. So thanks for your time.
Thank you.